Welcome to today's Explainer. We're going to go on a pretty amazing journey today. We'll start with those everyday magic tricks we've literally all done, like rubbing a balloon and sticking it to a wall, and we're going to travel all the way down to the fundamental mathematical rules that govern the invisible forces holding our entire universe together. Yep, today we are unlocking the mystery of electrostatics. Okay, let's dive into this and look at our roadmap. First, the mystery of static. Then we'll look at the nature of charge, how things actually get charged, the edge of electricity, and finally, the rules of attraction. Section 1. The mystery of static. Everyday magic. So think about running a plastic comb through dry hair. You've probably seen this. Suddenly, that completely ordinary comb can pick up little tiny pieces of paper, almost like it's defying gravity. What you're witnessing there? Well, it isn't magic. It's actually frictional electricity in action. And that brings us right to our core definition, electrostatics. Simply put, it's the branch of physics that deals with electrical charges at rest. So we aren't talking about the flowing currents that power your TV or charge your phone. No, we're focusing entirely on stationary charges. Charges that just build up and wait. Now, this is actually a really ancient mystery. Humans have been studying this stuff since way back in 600 BC. That's when the Greek philosopher Thales noticed that rubbing a piece of amber with wool suddenly made it attract light objects. Fast forward to the 16th century, and British scientist Dr. William Gilbert proved a bunch of other substances do the exact same thing. And then, by 1734, a guy named Taffet made a massive breakthrough. He figured out that even metals could be charged just by rubbing them with fur or silk. So we went from a curious little piece of amber to realizing, hey, this is actually a universal property of matter. Section 2. The nature of charge. Diving into the atom. So what's actually going on when we rub these materials together? Let's zoom way, way in to find out. Now, what's really interesting about this is the modern theory of electrification. See, atoms are naturally neutral. The positively charged protons and the negatively charged electrons, they perfectly balance each other out. But when two bodies rub together, that friction literally forces electrons to jump ship. So the body that loses electrons becomes positively charged, while the body that catches those extra electrons becomes negatively charged. It's the movement of electrons that does the whole trick. And these charges follow some pretty strict but fascinating rules. First off, like charges repel, and unlike charges attract. So if you rub an ebonite rod with fur, it gets a negative charge. Rub a glass rod with silk, it gets a positive charge. Bring them close together, and boom, they attract. Also, charge is a scalar quantity, meaning it just has magnitude, no direction. Plus, in an isolated system, charge is always conserved. Oh, and the total amount of charge? Totally unaffected by whether the object is moving around or standing perfectly still. Okay, now we hit a heavy-sounding physics term, the quantization of charge. But honestly, it's super simple. It just means that charge doesn't exist on some smooth, continuous sliding scale. It comes in specific, indivisible chunks. Think of it like steps on a staircase instead of a ramp. The total charge on a body is literally just a multiple of the basic unit of charge, which is a single electron. And that electron has a set charge of 1.6 times 10 to the negative 19 coulombs. You absolutely cannot have half an electron's worth of charge. It's impossible. To give you an idea of the staggering microscopic scale we're actually dealing with here, check out this number. 6.25 times 10 to the power of 18. That is the exact number of extra electrons you'd have to gather up to create just one single coulomb of charge. It's a massive, almost incomprehensible number of tiny particles working together. Section 3. How things get charged. Friction, conduction, induction. Let's move along and see how this all builds up and how we can actually manipulate these charges in the real world. There are three main ways to charge something up. First is by rubbing, or friction, which we've already talked about. Second is by conduction. That's when a charged body physically touches an uncharged one and the charge just flows right over. And third is by induction. Now, this one is probably the coolest because it happens entirely without any touching whatsoever. And this brilliantly illustrates exactly how induction works. Let's say we want to give a metal conductor a positive charge, totally contact-free. Step 1. We bring a negatively charged rod super close to it. This actually repels the conductor's own electrons over to the far side. Step 2, we ground that far side, which basically gives those fleeing electrons an escape route right down into the earth. Step 3, we disconnect that grounding wire, trapping the positive charge inside. And finally, step 4, we pull the rod away, the positive charges distribute evenly, and we've successfully charged the object without ever touching it. So you might be wondering, Why don't we notice ourselves getting highly charged all the time? Well, it's practically impossible to charge something just by rubbing it against a human body while holding it. Why? Because you and I are basically excellent conductors. The very second a charge starts to build up, it just leaks right through our bodies, straight down into the earth. Section 4. The edge of electricity, surface density, and points. Now that we know how we can manipulate these charges, let's explore where they actually hang out on these objects. So the crucial point here is that charges absolutely hate being near each other. Remember, like charges repel. If you dump a bunch of charge on a metal sphere, those charges are going to push each other as far away as mathematically possible. And that means they spread out entirely over the outer surface. There's this classic experiment where a charged sphere is fully enclosed by two uncharged metal hemispheres. When you pull the hemispheres away, all the charge has transferred to those outer shells. The inside is left completely, 100% empty of charge. Now, this specific behavior of charges leads to a really cool real-world safety question. Have you ever noticed that large trucks, especially the ones carrying highly flammable materials, often have heavy metallic ropes or chains just dragging on the ground behind them while they drive? Why in the world would they do that? Well, the answer comes down to friction. The friction between those massive tires and the road, plus the air rushing over the truck, builds up a huge amount of static charge. And if that charge were to just sit there and accumulate, a single spark could literally cause a huge explosion. Those dragging metallic ropes safely earth the charge continuously as the truck moves. But where that charge gathers is super interesting too. Thanks to something called the action of points, charge doesn't just spread out evenly on weirdly shaped objects. It concentrates heavily at sharp edges. The density gets so intense at a sharp point that it actually transfers charge to the air molecules nearby, repelling them and creating what's known as an electric wind. Crazy, right? Section 5. The Rules of Attraction, Calculating the Invisible Force. Okay, we've seen the everyday magic, the microscopic mechanisms, and the real-world safety applications. Now, for our final section, let's look at the underlying math. Pretty much everything we've talked about so far is governed by Coulomb's law. This is the rule that demystifies that invisible force pushing charges apart or pulling them together. It basically states two big things. First, the force gets incredibly strong as the actual magnitude of the charges increases. Second, the force drops off incredibly fast as things move apart. It's inversely proportional to the square of the distance between them. In a vacuum, this relationship is tied together by a massive constant called K, which is roughly 9 times 10 to the power of 9. But notice I said in a vacuum. What happens if those charges are sitting in water or air? Well, that introduces something called permittivity. Permittivity is essentially just a material's natural resistance to letting an electric field form. For example, water has a relative permittivity of about 80. That means if you take two charged particles in a vacuum and then drop them into water, the electrostatic force between them instantly drops. It becomes 80 times weaker. To truly wrap our heads around the sheer, mind-boggling power of this electrostatic force, let's look at a calculation straight from our source material. Imagine taking two alpha particles, which are basically just helium nuclei missing their electrons. If we calculate the gravitational pull they have on each other based on their mass, and then compare it to the electrostatic repulsion pushing them apart based on their charge, the result is absolutely astonishing. The electrostatic force isn't just a little bit stronger. It is 3.1 times 10 to the power of 35 times stronger than gravity. That is 31 with 34 zeros behind it. And that leaves us with a pretty profound mystery to ponder. If the electrostatic force is unimaginably stronger than gravity, literally 35 orders of magnitude stronger, why is gravity the only force you actually feel pulling you down right now? The answer is hidden in the perfect balance of the atom. But I'll leave that for you to explore on your own. Thank you so much for joining me on this explainer, and keep questioning the invisible forces around you.